Hello everybody and welcome to this Oceanography Final Exam Review Part 1. We're going to be going through a slog through your study guide, so get yourself ready. We're going to do about half the study guide now and we'll save the rest for another video. So without further ado, let's go on to your study guide. So first we start off with a little bit of philosophy of science, okay? You should know what it means to be empirical. Okay, so remember sciences are empirical, and that just simply means it's based off observation. Remember that observation, that's what science is all about. So that's why we often call these the empirical sciences. So oceanography is an empirical science, okay? Now, going to the scientific method, we talked a little bit about a hypothesis versus a prediction. So a lot of times people get this confused. That's why I have a question here about it. So a hypothesis is, it's an explanation. It's trying to explain how nature works, and it's kind of like a proposed explanation to propose how does nature work. A lot of times it's in a way of like formulated in a causal way. So like this happens because of X. So like for example, the trees lose their leaves in winter because it gets cold or because the daylight hours change or something like that. Okay. Now prediction is just very different. It's just a guess at what we think is going to happen in the future, right? It's just that people get these confused all the time. So they'll say, what do you hypothesize is going to happen? That's not a hypothesis. Hypothesis is trying to explain how nature works and why it happens the way it happens, okay? A prediction is based off a hypothesis. So based off my hypothesis, I predict, the leaves are going to fall off the trees in wintertime or whatever. Okay, so it's a guess at what is going to happen, what's going to occur. All right, what will be observed, right? Anyway, a big part of the part on philosophy of science in this class is I'm trying to just get people to understand that science doesn't answer every question, and it has limits, right? That's a big part of what it means to define something, means to actually set out what the limits are. So this question here, or actually this statement is false, right? It's not possible for science to answer every question, okay? Not every question is ultimately a scientific question. There's philosophical questions, there's religious questions, there's moral questions. These are things that we can't answer with science. We can't use the scientific method on them. We can't answer them by observation. Okay, we have to use other means to answer them. All right, now this is a very important question. This is going to be a short answer. Now, you know how your tests go. You get a question bank, right? Everything that you see on this study guide is at some point going to be on. It's going to be on the question bank. Okay, and you're going to get random drawing of like about 90 something questions from this bank, right? You're going to get 4 short answer questions, either between 4 and 6, I should say. They're 4 points each. This is one of them. That's going to be on the question bank. Okay, so you should be able to describe at least 3 criteria for something to be a valid scientific question. Okay, so what does that mean? That means that again, our goal here is to delineate what is science and what isn't. So things that we talked about in lectures, that scientific questions have to be about the physical world, okay? So it has to be something physical, observable, okay, something that's based on evidence, right? Evidence is what is evident. It's what's observable, what you can see, okay? So that's one part of it. Another part of this, that it has to be reproducible. Reproducible means that other people can come later and reproduce your observation, right? So if you observe the ocean's salinity in Corpus Christi Bay to be 3.5%, other people have to come and also make the same observation and verify that it's correct, okay? So that's what's meant by reproducibility. We also have falsifiability. That's probably the most difficult of these concepts, okay? To be falsifiable means that it can be proven true or false with evidence. So that means that you can use evidence, use what is observed, to prove something true or false. For example, if you had, let's say, someone hypothesized that invisible fairies, undetectable, totally unobservable fairies come and sprinkle salt into the ocean, and that's how the salt gets into the ocean. Well, that's not verifiable. We can't verify that, and we can't falsify that with evidence. Because why? Because we can't observe the fairies, right? They're not something that's physical and observable or generate any kind of evidence, okay? So that's what we mean by falsifiable. Be prepared when you come into the test day to have a question that is not a scientific question, and be able to write about it. So for example, you could say, just what I said, fairies come in the middle of the night and they're invisible, they're undetectable, you can't sense them in any way, and they come and they sprinkle salt into the ocean. That's how salt gets into the ocean. See, that's a question, or that's a statement that we can't prove true or prove false with science, okay? So have a question like that on test day you can come in and give me a question that science cannot answer or cannot verify or cannot determine, okay? I know that sounds ridiculous, of course, about fairies, but that's the point. So anyway, moving on. I hope that's clear enough for you. So getting on to like the basics of Earth and the oceans. What planets in our solar system have oceans? It's only Earth, right? Earth is the only planet that we know of that has oceans at all, or even much water. What non-planetary bodies of the solar system might have oceans? We talked about two in the lecture. That's Europa, which is a moon of Jupiter. And we also talked about Enceladus. Enceladus is a moon of Saturn, okay? Those are two non-planetary bodies or moons, okay? They revolve around a planet rather than the sun, whom they might have water, okay? What percent of Earth's water is in the oceans? It's actually about 97.2%, okay, or 97. So it's above 97%. So the vast majority of water on the surface of Earth is in the oceans, okay? What percent of Earth is covered with oceans? About 71%. Make sure that you know these numbers, okay? Because it's not going to be a multiple choice question probably. You're probably actually going to have to type in the correct number. Usually you have like 1 or 2 percentage point of error. So if you said 98% instead of 97%, or you said 96% or whatever, it'll probably still count that as correct. So don't worry too much about that. 5 oceans of the world. Make sure you know your 5 oceans. This is probably not, again, going to be a multiple choice. It's going to be something you have to type in, okay? Just type in the names of the oceans, okay? Because it would be too easy if it was just multiple choice. So, of course, you all know Indian, Pacific, and Atlantic, but don't forget the Southern, and don't forget the Arctic, okay? Now, moving on to the metric system. A lot of people get nervous about the metric system because you have math involved. Actually, you don't have to do too much math even, because a lot of the metric system conversions are just moving the decimal point. You can bring a calculator to the test. It's okay. You can also have some scratch paper and a pen. That's okay. You can't have class notes, of course. You can't have a book, of course. But anyway, you should be able to use a calculator if you want. Now, I don't know how much it'll help you, but know your base metric system units for mass, length, and time. Okay, for mass, that's kilogram. Length is meter. Time is seconds. There'll probably be multiple choice questions about that. I'll throw in some English system units to kind of confuse you. So, for example, what's an English system unit we use for mass? It's something like pounds or ounces, right? For length, we use miles or inches or feet or whatever. Okay, so those would not be the correct answers. So you want to know kilograms, meters, seconds. Those are metric system units. Of course, we use seconds in the English system as well, and that's okay. You should be able to convert between various metric system units. So remember, when you're converting metric to metric, it's easy because you're just moving the decimal point. All right, you could have a question like this. Not exactly like it, but numbers will probably be different. The units might even be different, but this would be something like this, okay? How many millimeters are in 11 kilometers? So we start off with kilometers, okay? Now remember that the way this works is we have our base unit, and we can scale the base unit up by tens. So we can go deca, hecta, and kilo, for instance. And every time you go up that scale, you go up by 10. So it goes 10 to 11 to 100 to 1,000. Okay, so you go up by a scale of 10 every step. You can also scale that base unit down, make it smaller. So you could have a deci, a centa, or a milli. Okay, and milli is 0.001, centa is 0.01, and deci is 0.1. Okay, and the base, of course, is 1. That's the base unit. It's just itself, 1. So anyway, when we go from kilo to millimeter, we have to go 1, 2, 3, 4, 5, 6. We make 6 jumps. So that means we're going to take 11 and we're going to move that 1, 2, 3, 4, 5, 6. And if you fill in the zeros, you notice that we'll have about 11 million. Well, we won't have about 11 million. We will have exactly 11 million. Okay? So that's how that works. Now, so I would suggest to you memorize this, what I just put right here. Okay, milli, centi, deci, base, deca, hecta, kilo, and if you want to come up with a mnemonic device or whatever, but just make sure you memorize that. And you know it goes 1,000, 100, 10, 1, 0.1, 0.01, 0.001. Okay, and then you can write that out. If I were you, I'd just write that out on my paper like a mind dump, and then you can move. You can do these conversions easily. Okay, there won't be a lot of these questions, maybe 1 or 2 or maybe 3 on your test. Okay, that's it. Now you should also have some kind of sense of how to convert English units to kilometers, or I'm sorry, to metric system. Now you're not going to have to do an exact calculation, but I want you to have like a ballpark sense of how much a mile is in kilometers, how much a kilogram is in pounds. Okay, so you should have some sense of that. It's going to be multiple choice. It won't be a numeric answer, so you'll be able to choose among whatever 4 or 5 options. So just good thing to memorize, there are 2.54 centimeters per inch. It's enough to just say 2.5 centimeters per inch. Okay, there's about 1.6 kilometers per mile, 2.2 pounds per kg, and 3.28 feet per meter. Okay, you can use those to get a general sense. Okay, so for example, if I ask you how many kilometers are in 10 miles, well, it's going to be 16, right? Because it's 1.6 kilometers per mile. So times 10, that's 16. And the other options, the incorrect options would be like 10, 1, 300 or something. Okay, so just they'll be way off. So just make sure you have a basic sense of that. All right, going on to basic geography. Okay, this is where we talk about latitude and longitude. We talk about also how the Earth is structured and how the grid system that we use. The line that divides Earth and extends from poles to other poles, those are called meridians. Okay, so remember that every meridian starts off, we drew Earth here, right? Starts off at one pole and goes to the other. Okay, starts off at one pole, goes to the other. So it kind of ends up looking like, I don't know, a cantaloupe or an onion or something like that. Okay, those are the meridian lines. Now, the 0 degree meridian line is the one that goes through, Greenwich, England, right? So Greenwich, UK. Okay. Do meridian lines intersect? Yeah, they do, at the poles. Okay, they all intersect at the poles, actually. Parallels don't do that, right? Parallels don't intersect at all. They're parallel. That's why we call them parallel. Okay. Now, what's the climate like at high latitudes? Okay. At high latitudes, that means up to 90 degrees north or south, it's going to be cold. Anything that is above, so it's greater than 66.5 degrees north or south, is going to be cold. All right. Anything that is between 23.5 north or south is going to be tropical. So those are the tropics. Remember, the tropics are at 23.5 north-south. Tropic Cancer is north. Tropic Capricorn south. Okay. Now that is connected all to the rotational axis tilt. So remember that our rotational axis is tilted. It's about 23.5 degrees right now, relative to the ecliptic plane. Okay. Remember, and what's the ecliptic plane? Remember that as we rotate around the sun. So here's the sun. Here's our orbit. There's Earth, okay? The ecliptic plane is this line of orbit around the sun, okay? So it contains our orbit. So our axis is tilted, 23.5 degrees away from perfect perpendicular relative to that ecliptic plane. All right, now in the diagram below, you could have a diagram like this, and it could be labeled like A, B, C, D, something like that. And it would ask you like which one of these depicts the winter solstice or the summer solstice or whatever. Okay, how do you determine what's the summer solstice? Well, the easiest way to do this is look at it and just figure out like, this particular position is the summer solstice or whatever, and then from there you can figure out what all the other positions are. So, for example, this one right here, this is the summer solstice. How do you know that? Because if you look at the North Pole is actually tilted towards the sun, right? Do you see how it's tilting towards the sun? Okay. This one, on the other hand, is the winter solstice here, D, because it's tilted away from the sun. All right. Now, because the Earth goes counterclockwise, you can figure out everything. Goes counterclockwise around the sun. You can figure out everything else from there, right? So this is the winter solstice. The season after winter, of course, is the spring. So this is spring equinox, and then over here, this must be the autumn equinox, right? So make sure you know all that stuff. Be ready to get a diagram like that and be able to label it. Okay. All right, now moving on to the origins of the oceans. This goes back through a little bit of history of the universe, history of the solar system, history of Earth. Gives you a little bit of background to understand where we came from and how the oceans got to where they are. Now, the Goldilocks zone. The Goldilocks zone refers to a part. You know the story of Goldilocks, right? It's not too hot, not too cold. It's just right. The same way, Earth is at just the right distance away from the sun to maintain a stable orbit and have a liquid water ocean, right? So if you're too close, if you're too far away, if the orbit was unstable or whatever, we would not be able to maintain that liquid outer, shell of water. Now, briefly describe with a single sentence or two, what is the Big Bang Theory states? So the Big Bang Theory states that, giving you just brief history of the universe and solar system and Earth. It starts with the Big Bang, right? Big Bang is this particular point in history in which there was all matter, time, energy, and space came into existence. And from there, space has been rapidly expanding at the speed of light every direction. Okay, so from that point, space came into being, time came into being, matter, and whatever else. Okay, so that was about 13.7 billion years ago. Okay, so we've used GA, that means giga-annum. You can also use BYA, that means billion years ago. Okay, so 13.7 billion years ago. Now, at that moment of the Big Bang, what was mostly in existence? I shouldn't say at that moment, but let's say minutes after the Big Bang. It was mostly hydrogen, right? So hydrogen is the predominant element of the universe as far as we know, not including things like dark matter, but as far as we know, hydrogen is the main and predominant element of not only the universe but of the solar system too, right? So solar system, the sun, what is it mostly made of? Hydrogen. Okay, it's the smallest, most simple element that there is. Okay, element number one. Now, what isotope of what element synthesized by hydrogen burning process? So remember that all the solar energy that we receive is created, not all of it, but almost all of it, created by this hydrogen burning process. So that's where you have hydrogen combining with hydrogen, four of them actually, to give you what's called helium-4. So helium-4. So helium is created by what's called hydrogen burning, and that's where four hydrogen atoms combine to form a new element, helium-4. It's called an alpha particle. Now, that process produces most of the solar energy in our solar system. Okay, so that answers the next one. What is the source of the solar energy? Where's it coming from? It's coming from hydrogen burning. Okay, in our sun. Now, what planet in our solar system orbits within the ice line, which are outside of the ice line? So remember that there's an ice line, or sometimes it's called a frost line in our solar system. So we have the sun. Okay, there's happy little sun there. And then you have a few planets, actually 4 planets that are terrestrial. That includes the Earth. That's the third rock from the sun, right? It's the third planet from the sun. And then there's what's called the frost line. Okay, I'm going to put frost line or ice line, whatever you want to call it. And then you have the Jovian planets, or the large ice planets, gas planets that are on the outside. So the planets in the inside of the ice line are, right, they're the terrestrial planets, they're the rock and iron planets: Mercury, Venus, Earth, Mars. When you get past the frost line, then more volatile elements can condense. Lighter elements like hydrogen, helium, carbon, so things that are like methane, carbon dioxide, et cetera, can condense at that colder temperature outside the ice line, and then you get larger planets, significantly larger planets. You get Jupiter, right, Saturn, Uranus, and Neptune. Okay. So how does the composition of planets vary with the different ice lines? So I just explained that above, right? So outside of the ice line, on the outside end of the solar system, past the ice line, you get planets that are composed mostly of lighter elements. So again, things carbon, oxygen, helium, hydrogen, et cetera, okay? Whereas within the ice line, the planets are composed of heavy elements: iron, silicon, magnesium, etc. Okay, what are two different hypotheses for the origins of Earth's water? So there are two competing hypotheses, and maybe both are true, right? It could have a combination of the two of these. But you have Earth. The first hypothesis, that Earth in its early history was struck by comets, right? So comets are these balls of basically dirty snowballs. You could think of them, right? They compose of light elements, including water, and dust. So they struck Earth. Now, make sure that you say in your answer, and by the way, this could also be a short answer question on your test, right? So make sure that you explain in your answer that there's a difference between comets and meteorites. Okay, so these are not meteorites. Meteorites are stony or iron material. Comets are not. Comets are, again, composed of lighter materials like water and carbon dioxide. So one is from comets. Two is that there was volcanic outgassing. So volcanic outgassing, that means that there was a lot of water contained in the minerals that accreted together to become Earth, and they have slowly outgassed from the mantle over time. Indeed, we think that probably only 50% of the water of Earth has been released from inside the Earth. There's actually quite a bit of water still trapped down there, we think. All right, now what was Earth's earliest atmosphere like? Was there oxygen? And the answer to that is no. There wasn't oxygen. And why wasn't there oxygen? Is because there was no photosynthesis early in Earth's history. Okay, it took time for that photosynthesis process to evolve so that you could actually get free oxygen building up. What are four differences between continental crust and ocean crust? So that's another important thing you have to know here. And this is another thing I can often ask as a short answer question. Okay, so be prepared to give a response here. Again, 2, 3, 4 sentence response. First of all, continental crust, ocean crust, right? You have the oceans, for the most part, are underlain, for the most part, by ocean crust. Now, ocean crust is denser. So it's about 3 grams per cubic centimeter versus 2.7 grams per cubic centimeter for the continental crust. It's also, generally speaking, younger. So ocean crust is only really maybe no more. I can say that it's less than 180 million years old. Okay, less than 180 million years old. Whereas the continental crust on average is about 2.5 billion years old. Okay, much older. So ocean crust is younger. Ocean crust is denser. Ocean crust is also, we can say it's also, this is obvious, but it has a lower elevation, right? Okay. And another thing that we can put here is that this ocean crust is mostly made of a rock called basalt. Okay. Whereas the continental crust is mostly made out of a rock called diorite. It's a little bit like granite. Okay, so there's different rock types. Basalt, you should know that basalt is the dominant ocean crustal rock. Moving on to the Great Oxygenation Event, kind of what I referred to up here. At some point, photosynthesis evolved in Earth's life's history, and that's when we had the Great Oxygenation Event, when free oxygen was able to start building up in Earth's atmosphere. Now, why do we think, scientists think that Earth is about 4 billion years old? Where do we get that number? That number is based off of radiometric dating, which is explored in your book in more detail. I don't talk about too much in your lecture, so it's something you should maybe go read about in your book. But radiometric dating is when you use isotopes of radioactive elements, and you can figure out from the rate of their decay how much time has elapsed since that rock formed. So we use radiometric dating to date the Earth, and we figured out it's about 4.5 billion years old. By the way, if you date meteorites, if you date the moon, you get about the same age. All right, moving on to history of marine science. So what are some of those ancient civilizations that engaged in ocean exploration? So this is BC times, right? So those are things like civilizations. I'm sure you've heard of the Greeks, right? The Egyptians. We also mentioned the Minoans, which were based on the island of Crete in the Mediterranean. Also the Phoenicians. The Phoenicians were a civilization similar to, maybe from the Bible, you maybe heard the Philistines. Okay, there's a similarity between those two cultures. But they're living on the coast, on the eastern coast of the Mediterranean, in what is modern-day Israel, okay, or Palestine. What was significant about the Library of Alexandria in the development of marine science? Remember that the Library of Alexandria was located, again, at Port of Alexandria. It's in modern-day, it's still there in modern-day Egypt, near the Nile Delta, in the south of the Mediterranean. And at this library, ancient library, right? This is, again, before Christ, before BC times. In this library, every single ship that came into port had to turn over charts and maps that it held in its possession. So those copies were made at the time. When they handed over the charts and maps and whatever else, books, whatever, copies were made, and then they were returned. And by those means, it was able to, the library was able to build up its collection and become a huge center of knowledge. So it was a huge, maybe you could just say it was a huge center of knowledge for the ancient world. What was a major contribution of Ptolemy of Alexandria to marine science? Now, Ptolemy was a scientist. There's actually a lot of famous Ptolemies, people named Ptolemy that were scientists. But Ptolemy of Alexandria, in this case, because it was, again, first century scientist, and he used all the charts and maps that were available in the Library of Alexandria to put together a very complete map of the Eastern Hemisphere. Okay, so he made the first map that really showed almost in great detail a lot of the Eastern Hemisphere. Of course, the Western Hemisphere had not been mapped yet by Western civilization, so we had to wait for that till the Christopher Columbus times and the Renaissance. But what historical event took place in 1453 A.D. that was very, very important to a renewed interest in ocean exploration? So jumping ahead 1,400 years, what happened? It was the fall of Constantinople. At this time, Constantinople fell to the Ottoman Turks. It was defeated, and that was an important port. It was an important waypoint for people trying to gain access to the Middle East and to the Far East for trade. When Constantinople fell, it cut off land-based means of getting through to the Middle East and to the Far East. So it made transportation and trade much more difficult to Western Europe. Okay, that meant that Western Europeans became very intent in sailing and looking for new ways and more sophisticated ways of sailing, so that they could gain those trade route access to the Middle East again and to the Far East. Okay, so that's what took place there. That's what created what kind of gave an impetus for the age of exploration in the Renaissance, and led ultimately to the discovery of the New World for Western Europe. Okay, who are some of those primary ocean explorers in that time, in that age of exploration, the Renaissance and after? It was, of course, Christopher Columbus, but also there was Magellan, there was Prince Henry the Navigator. There are a lot of famous figures that I'm sure you've heard about before that were doing this ocean exploration and eventually led to locating Western Europe, locating or rediscovering the New World, right? Okay, so how did ocean navigation? How did they determine their latitude and longitude before things like GPS? Okay, the way that this worked is they had a tool called a sextant, and a sextant was just like an eyepiece, kind of like a telescope, and it had a kind of like a protractor down here that had the degrees, right? And then it just had a little piece of string with a bob that hung, and then by pointing your sextant at some kind of astronomical, like let's say you were looking at a star, you could pinpoint that star and you could see how many degrees it is above the horizon. Well, you can actually do that with Polaris, the North Star, and you can figure out the number of degrees that it is above the horizon is the latitude, your current latitude. So they could determine their latitude from the North Star. How do you figure out your longitude? Well, you know how time zones work, right? It's the same principle. So they actually used a clock, right? Just a simple clock that Of course, it had to be very precise. And what they did is they set it at noon. They set, okay, we're going to sit here in Greenwich, England. We're going to set the clock so that noon is exactly when the sun is 90 degrees up in the air, or not 90 degrees up in the air, but at its highest point. Okay, we have noon. Now we're going to start traveling, and they would keep track of when noon was, when the sun was in the highest point in the sky relative to when it was in Greenwich, England, right? And based on that, if it was, for example, rose at now 1 p.m. instead of 12 p.m., then that you went 1 hour of change would be like 1 hour time zone, right? So you know that there was 15 degrees of change in your longitude. So 1 hour of change in that is equivalent to 15 degrees of longitude, okay? So that's how that all worked. So basically they're using a sextant and they're using a clock to keep exact pinpoint their latitude and longitude. All right, now, what year was the HMS Challenger expedition? So, the HMS Challenger expedition was in 1872 to 1876. Okay. Two major modern oceanographic research vessels in the modern day age. That's the Okeanos Explorer. That's a U.S. vessel. And there's the Japanese Chikuyu. Okay. These are again billion-dollar research vessels, and they're very sophisticated. And what exactly do they do? So that's the next thing. Both these research vessels, they do offshore drilling. Okay, so they can drill down while they are floating on the surface of the ocean. They can send down a drill bit and drill the bottom of the ocean. So they do offshore drilling. They do also. You might remember those ROVs. Those are remotely operated vehicles. Okay, they also have, so those are like remotely operated submersibles, and they also do echo sounding. And the kind of echo sounding that they do there is multi-beam. Okay, it's called multi-beam. All right, and now something that, of course, the research vessels don't do this, but it's another technology that we use highly in oceanography, is satellite altimetry. Okay, satellite altimetry uses satellites to determine the height of the ocean water, so how high the ocean surface is, and from there they can determine the depths of the ocean. Okay, because remember that there's a gravitational effect from the shape of the seafloor on the height of the water level directly above it. Okay. Moving on to plate tectonics. Is Earth's mantle solid or liquid? The answer is it's a solid. Okay, it's absolutely solid. However, it does have some liquid-like behavior. That's what allows it to convect. Okay. What powers that convection that we find in the mantle? It's the geothermal gradient. Okay, so geothermal gradient. What does that mean? That just means that it's, if you're looking at, okay, this is the crust, right? And here's the core. and here's the mantle. Whoops. Here's the mantle. The core is hot, okay, and the crust is cool, and there's going to be convection as the Earth tries to cool off. So remember that plate tectonics is all about Earth just trying to cool off. It's just Earth's cooling system, okay? Now, what's the difference between asthenosphere and lithosphere? To think of the difference between asthenosphere and lithosphere, it's the lithosphere is the uppermost mantle plus the crust. Okay, so looking again at, if I was going to draw this out, right? So here's the Earth, here's the core. Okay, here's the mantle. Okay, the lithosphere is maybe like this. All right, it's this uppermost mantle plus the crust. The asthenospheric mantle be down here. It's the lower mantle. Okay, they're lower below the lithosphere, and this is the part that can convect. The asthenosphere convects, but the lithosphere does not. It's too cold to convect, so it behaves more like a. I always think of like the difference between the lithosphere and the asthenosphere is like cookie versus cookie dough. So the lithosphere is like a cookie. It breaks, it crumbles. You know, it behaves like a rock, like you're used to. Whereas the asthenosphere behaves more like cookie dough. It's malleable. Of course, cookie dough doesn't convect, but it can move and form and deform and bend, etc., etc. Okay. All right. Now we talked a little bit in this class about Alfred Wegener. So he's the gentleman who introduced this idea of continental drift in a serious way to back up his claims. By the way, this is another good short answer question, so be prepared to answer this. So Alfred Wegener argued for continental drift by bringing up 4 lines of evidence. Okay, first thing is that continental margins, so the coastlines matched. So that means that the continents can kind of fit together. You can piece them back together almost like a puzzle, especially if you take into account the shape of the continental shelf. Okay, not just the coastlines. Another line of evidence came from glaciers. So glaciers leave a lot of striations and scratches and grooves as they flow over the surface of the Earth. And it shows you what direction the glaciers were moving in when they were formed. So when you come back and you piece the Earth back together, you put all of the continents back together as Pangea, you find that those glacial striations match up. Okay, so the directional indicators that were left by the action of glaciers over Earth's history match up. Okay, the direction, the line, they line up is another way to say it. Another thing is from matching rock units. Okay, so if you and also mountain belts. So if you put the continents back together as Pangea, you notice that rock units on different continents match up. So you find the same exact rock and the same exact mountain belt on multiple continents. Okay, so again, when you put them back together, you piece them back together, everything matches up and lines up. We also find matching fossils. So again, looking at fossil species, we take a look at Glossopteris, or there are a lot of different animals, Mesosaurus. There's also Cyanonathus. Okay, there's these different fossil species that we find on multiple continents that could not have possibly swam across the Atlantic or the Pacific. Okay, so they probably got there continents were connected, they were surviving on that Pangea continent that broke apart, and that's why we find multiple fossils, the same species, on different continents. What drives that seafloor spreading? Continental drift, all plate tectonics. That's mantle convection. Okay, so it's the fact that the mantle is convecting due to the geothermal gradient. The fact the core is hot, the surface is cold, and that's what creates the convection. Where on Earth is new seafloor generated? Where is it destroyed? Very important. Seafloor is generated at mid-ocean ridges. We talk about a lot in this class. It's destroyed at subduction zones. The trenches, okay? Trenches. Now, approximately how fast do plates move? They move about anywhere between 1 to 10, I don't know why I wrote a 9 there, 1 to 10 centimeters per year. All right. Now, going on to ocean basins. So Ocean basins, the ocean floors, we study those using a subject called bathymetry. Bath just means depth. Okay, metry means measurement, so we're just measuring the depths of the ocean. When we measure the depths of the ocean, we find that, of course, we have the abyssal plains, we have mid-ocean ridges, we have continental. So we have these different main provinces that we're going to talk about in this part of the class. So now you know that the HMS Challenger voyage, they made some bathymetric measurements. Okay, they did sounding, what's called sounding measurements. How did they do that? Very simplest way. It's a weight on a rope, right? So they had a weight, they had a rope, they dunked it down into the water, and however far it went down, that's how deep it was. Okay. Now, how does echo sounding work? So echo sounding is a different way of measuring the depths of the ocean. The way it works is that a acoustic wave is generated. It travels through the water, and eventually it hits the bottom, and it bounces back. Okay. Now, the time that it takes to bounce off of the ocean bottom and return, that we can figure out the depth from that by knowing the speed of sound in water, which is about 1450 meters per second. Now, that 1450 meters per second is not constant. It actually depends on different things such as the salinity, the density, the pressure, and the temperature as well. Okay, but you don't have to know all that stuff. I mean, you don't have to know exactly how it changes with all those different variables. I just want you to know that it does change. So you can get, as a rough estimate, a pretty good idea about the depth of the water just by using a straight number, 1450. It does change a little bit with density and all those other factors, but not a lot. Okay. Now, which lady from Ypsilanti, Michigan was instrumental in compiling the first global map of the seafloor? That is Marie Tharp. What are the three provinces of the ocean floor? All right, so if you look at the ocean floor, first of all, you have the continents, right? And here's let me draw the ocean, kind of the ocean sea level. All right, so I'm going to draw the sea level like this. And I'm going to draw in so these are the continents, right? So I'm going to put CC for continental crust. And we're going to have OC for ocean crust, okay? Now, in the middle of the ocean there's a ridge, okay? That's the mid-ocean ridge. And then it goes to these parts that are called the abyssal plains. So the abyssal plains are the very deep parts. These shallow parts where the ocean is underlain by continental crust, that's called continental shelf. Okay. Now, what is the difference between passive active margin? So we might have so this would be like a passive margin here, okay? An active margin, there would be subduction going on. So I'm going to draw the ocean crust, right, subducting into the mantle. And in that point, you get a trench. Okay, so here's the continental crust again. I got to make it above sea level. But here you have a trench at the active margin. This is where active plate tectonics is taking place. Subduction zones, for example, are active tectonic margins. You're going to get volcanoes brewing here. You're going to get earthquakes, and you're going to get pretty small. You're going to get a pretty small continental shelf. Okay, so here at these kinds of boundaries, it gets deep very fast. The continental shelf is not very wide, and then it goes into the trench, which is the deepest parts of the ocean. Okay. On the other hand, on a passive margin, okay, so on a passive margin, you have these very developed continental shelves, wide continental shelves. Okay, so it gets deep at a much slower rate. So, example, Gulf of Mexico, right? The whole Texas coastline is all passive. A place that is for example, active would be like our West Coast, right? So maybe passive, think of Texas, versus active, think of our West Coast, where there's earthquakes, there's volcanoes, there's a trench, right, et cetera, et cetera. Think of the West Coast, California, Oregon, Washington, etc., all the way up to Alaska. Okay. Now, where are continental shelves more developed? They're more developed along passive. Okay, so passive margins. Trenches are found at active margins. Okay, where's the deepest place in the ocean? It's in trenches. Okay, and specifically, it's in the Mariana Trench, and that is called Challenger Deep, right? So, the deep point of the ocean, we call that Challenger Deep, is located in the Mariana Trench off the coast of Guam. Okay, so it's in the South Pacific. Why are trenches so deep? It's where the ocean crust is sinking back into the mantle. Okay, so you would imagine it'd be very deep. Okay, this ocean crust literally sinking back in the mantle. It goes all the way down, by the way. That ocean crust is going to go all the way down to the core. It'll literally sink all the way down to the core eventually. All right, why do volcanic islands often form around subduction zones? So this is because when water gets into the mantle at subduction zones, it lowers the melting temperature. So water causes the mantle to melt. And that's what causes the volcanism that we encounter there. Those chains of volcanic islands are called island arcs. Okay, arcs. Black smokers are the hydrothermal vents that you find at mid-ocean ridges. Okay, the smoke is made out of a lot of iron salts, especially like iron hydroxide and also iron sulfide. Okay, so that smoke you see is really precipitation. It's precipitated grains. Okay, and that becomes eventually hydrogenous sediment, as you know. Now, how do hotspot chains like Hawaii work? You probably shouldn't worry about this one too much because this is a little bit you can kind of scratch that one out. For these two, you can forget about these seamounts and hotspot chains. It's okay. So I didn't put those on the test. Okay. Anyway, moving along. Going on to sediment. So we'll finish sediment here, and then when we're done with sediment, we'll stop and we'll do the next part. Okay. So anyway, ocean sediment. What are 4 things that can constitute sediment? There's a lot of different stuff. For most important though is rocks, minerals. Okay, that's the most important type of sediment that can be sediment, rocks and minerals pieces. Okay, the next thing is shells and tests of marine organisms. Right, all that plankton produce shells and tests, microscopic usually, that drifts down to the bottom. That can become sediment. There can also be precipitated grains. So these are minerals that are precipitated at like mid-ocean ridges. Okay, that can constitute sediment. You can also have things like volcanic ash. You can also have things like cosmogenic material that comes from outer space, from meteorites, etc., that blow up in Earth's atmosphere. So those are more rare things, but you can have stuff like that as well. All right, what are some of the ways sediment ends up in the ocean? So what are processes that take sediment from the continents and put it into the ocean? So those are things like basically wind, water, ice. Okay, so the wind can blow abyssal dust. So wind brings abyssal dust into the deep ocean, right? Think of like the Saharan dust that blows off the Sahara can be carried very far into the deep ocean that way. You can have water, which run off from the continents, rivers, brings sediment into the oceans, okay? You can also have ice, because ice, glaciers, actually do a lot of damage to the continents. They erode the continents mightily. And all of that sediment ends up in the ocean as the glaciers, what's called calve off at the glacial front. they become icebergs and they release that sediment. So wind, water, ice, glaciers, that all can deposit material from the continents into the oceans. In terms of deposition, what does energy of the environment refer to? It refers to how much water movement there is near the bottom. Okay, so water movement near bottom. So of course the sediment's going to get deposited on the bottom of the ocean. Okay, now where the water is shallow near the coastlines and you have the waves perturbing the bottom, right, perturbing the ocean floor, there's going to be a lot of water movement. And so when the water's shallow, you end up with very high water movement, very high energy. When you have very deep water, there's not very much water movement in the deep ocean floor, okay? Because we'll learn later, right, or we have learned, I guess, already, about deep water currents. Most of the currents are happening, and most of the waves, of course, are surface, but most of the currents are happening in the top, like 10% top of the 400 meters of the ocean, okay? There are some currents that happen near the bottom, but not much. So the deep ocean, it's going to be low energy. And the shallow systems are going to be typically high energy, except think of things like back bays like we have here in Corpus Christi. Back bays that are protected by wave action actually are pretty low energy. So when you have low energy, you tend to get very fine silt and clay. When you have high and ooze, when you have high energy, you tend to get cobbles, gravel, sand. Okay, so sediment like what's sediment size like near shore? Again, higher energy typically. You get sand, silt, gravel, cobbles. Okay, what's sediment size like in the deep ocean? Silt and clay. It's fine. Okay, so fine versus coarse. In terms of sediment classified by source, what is terrigenous sediment? It's the sediment that's washed off the continent. Okay, it's the stuff that's terra, it means earth. Okay, terrigenous means continent derived. Biogenous sediment, on the other hand, is authigenic. Authigenic means self-created. The ocean has created this material itself. It derives from itself. So biogenous sediment is the shells and tests of marine organisms that build up over years. What are plankton? Now, this is, of course, very annoying. You can notice that brilliant Microsoft Word has said that it says, actually, if you click this, you'll see it suggests I should say, what is plankton? That is grammatically incorrect. Actually, it's not what is plankton, it's what is our plankton. Plankter is singular, and plankton is correct. Okay, so that shouldn't be underlined. They don't know what they're talking about. But plankton, what are plankton? Plankton are any kind of organisms that freely float in the water and are carried by the currents and the wind. Okay, it could be anything. It could be the microscopic algae. It could be like sargassum seaweed. It could be jellyfish. But the main point is that it gets carried by wind and currents. Okay, the vast majority of plankton consists of algae and microscopic protist type organisms that are too small to sink to the bottom. Because remember that if you're photosynthetic, you want to be near the top where the sunlight is. So you want to be very, very small so you float. Okay, so that's the idea. The plankton float for the most part near the surface, and they drift along with wind and currents. Okay, that's what plankton are. Now, what are some different forms of plankton that produce shells? Talk about some different kinds. There's coccolithophores. There are dinoflagellates. There are foraminifera. There are diatoms and radiolarians. Diatoms and radiolarians make their shells out of silica. Dinoflagellates make their shells out of chitin. Chitin is like the exoskeleton of an insect, for instance, whereas foraminifera make it out of calcium carbonate. Okay. This means that when coccolithophores and foraminifera die, they're going to produce a calcareous ooze, a carbonate-based ooze, whereas diatoms and radiolarians die, they're going to produce that siliceous ooze. Okay. So what happens to shallow microorganisms after they die? Oh, also cold water. Diatoms and radiolarians are more adapted to colder water environments. What happens to shells of microorganisms after they die? After they die, they sink to the bottom. Okay, and they become sediment. They become either calcareous ooze or siliceous ooze. Now, what's neritic versus pelagic sediment? Neritic sediment and pelagic sediment. So neritic just simply means near shore. Pelagic simply means deep water, far from shore, okay, the deep ocean. So deep water. Turbidites are big. These are things that occur in submarine canyons, and they are maybe you can think of them as kind of like an underwater avalanche of heavy sediment-laden water that comes streaming down these submarine canyons on the continental shelves, and they carve out the submarine canyons. Okay, so they're very distinctly connected, characteristic of submarine canyons. Okay, submarine canyons are carved out by turbidites, okay, by turbidity currents, which when they settle on the bottom become turbidites. They leave turbidite deposits. Okay, and these are neritic deposits. They're near shore deposits of sand, silt, clay, gravel, things like that. All right. Now, what is calcareous ooze made of? It's made out of calcium carbonate. Okay, and remember, it reacts with acid. Okay, so calcium carbonate, CaCO3. The source of that chemical constituent is, of course, the calcareous ooze. The chemical constituent, calcium carbonate, is made of the coccolithophores and foraminifera shells. Okay, the shells of the plankton organisms. The CCD, that is the calcite compensation depth, or the carbonate compensation depths. Okay, the CCD is the point, the depth below which the water has become so acidic that, because remember, carbon dioxide dissolves into the water, becomes carbonic acid, and it dissolves, more carbon dioxide is dissolved at higher depths, greater depths, okay? And part of the reason, we talked about this in the class, part of the reason has to do with the fact that a lot of the life, that photosynthetic life that exists in the shallow water in the photic zone is using up that carbon dioxide. You don't have that in the deep water, right? Because there's no sunlight, there's no photosynthesis. Calcium carbonate is going to start dissolving at a deep depth because there's too much carbonic acid. So the calcium carbonate, the calcite, is going to start getting eroded away and dissolved away faster than is supplied below the CCD. Okay, so once you get below the CCD, calcareous ooze can no longer build up. All right, going on to siliceous ooze. Siliceous ooze is made of the shells and tests of silica-based planktonic organisms like diatoms and radiolarians. Now, the chemical formula of that is SiO2. This silica is not so susceptible to carbonic acid. However, it is, because silica is very depleted in the ocean, it often dissolves. So there has to be a very heavy supply of silica from radiolarians. So a lot of production of radiolarians and diatoms to produce the silica to outrun the process of dissolution of the silica into the ocean. Because remember, the silica in the ocean is very depleted. Why is carbonate ooze and siliceous ooze generated in the near surface waters? It's because it comes from plankton, the photosynthetic plankton, and they need sunlight to survive. So they're in the photic zone, in the surface waters. They are doing their photosynthesis, they die, and then they drift down to the bottom. Okay? We're on number 78 now. We finished ocean sediments. I'm going to cut it off here. We've already been going on for an hour. I will produce another video, a part 2, and we'll talk about the rest of this study guide, getting you prepared for your test. Okay? Just let me know if you have any questions or concerns about this class or the test, and I'll talk to you next time.